Okay, so when we do our Lewis structures, like we did yesterday where we found formal charge and tried to determine the best one, when you do that, sometimes you'll see you can't really determine a best one. They all kind of turn out the same because you're not really having different different atoms in there, you're just moving where the bonds are. So it makes it difficult to pick out a dominant structure. So sometimes there are molecules and ions, I should say not and, I should say and or ions, where the experimentally determined Lewis structure or arrangement of your electrons I would say is not adequately described by one structure only. Or maybe it would be better here if I said single structure. So I can't just use one single structure to describe them. Now, we're going to work through this with, or I'm going to have you move and work through this with ozone. What's the chemical formula for ozone? O3. And I'm going to tell you, and we'll learn this after we quiz over all the stuff we've been doing the last few days, we'll move into actual molecular geometry. But I'm going to tell you it is a bent molecule. And what that means is I have a central atom, trigonal planar, I have a central atom and my oxygens come off at a bent angle. So all of your arrangements are going to be bent. But what I want you to do is to find all possible Lewis structures and all formal charge. So go ahead and move to your lab stations, and I want you to work through that with O3. See how many you can find and calculate the formal charge on each oxygen and then the formal charge on the whole molecule for each structure that you determine. And then we'll go through it together and see if you get what you should. I picked kind of an easy molecule for the first one. Okay. When you've got them, come back to your desks and we'll talk about them. When you've got them, come back. Be sure you do formal charge. Make terrible ones. How many do you have?
Huh?
How many structures do you have?
We just have two.
Two. Simon, how many structures did you guys have? Two. What about you guys, Seneca? Two.
Because when you do more than one, don't you have to have the same amount of bonds? They can just like change between which ones?
In some cases, yes. In other cases, no. Like if this were a polyatomic ion that had maybe 3 different elements,
Okay.
you might be able to do some different things with it.
Okay.
But because of the way this one is set up, you can do 2.
Because that's how it was yesterday with the thiocyanate or thiosulfate.
Yes, because it's another, but that was more, yeah.
And instead of doing the one.
Rarely will you have over 3. Sometimes you might have 4, but rarely. How many did you guys have, Caitlin? 2. Carly? 2. Okay, see if they look like this. Or similar to this. My lines are not great today. Now, one of the things that I tried to show, but now that I look at it on the screen, you can't see it as well. What happens when I'm drawing these is when I have a single bond, the distance between the atoms should be greater than when you have a double bond. Think about that. The more bonds you have, the greater the attraction of those for each other. So the shorter they become, the more they want to hold on. Way back in Chem 1, we did that lab with toothpicks. I think that was Chem 1. Toothpicks, and you wrapped them together. When you had a triple bond, it was much harder to break than a single bond. So we represent that a little bit. Did you calculate formal charges on both of them? Okay, what did you do? I called this resonance structure 1. I don't know if yours looks just like mine or not, but Jackson, what did you guys get for formal charge on this one? 0. Haley, what did you guys get for formal charge on the other one? 0. So both of them have a formal charge of 0, so that really doesn't help us out at all. So when you get to a point like that, you can say that a single structure can't be dominant. Why not? Look at those. Why isn't one dominant?
Because they're the exact same thing.
All we did was flip a bond, right? And that happens a lot of times. I would say because bonding is the same. I also have 3 of the same atom, so I don't have any electronegativity differences I can look at. Sometimes that makes a difference. I don't think we need to say really anything else other than that. So we'll talk about what happens when it's like this. So when I have no reason for one structure to be dominant over the other, and for this one I would say electronegativity, this is another defense, electronegativity is the same for all. Because all atoms are identical. So these would be considered equivalent structures. And that's what I would call them. We have no dominant structure. When we have no dominant structure, you see what I did in the middle of mine, how I made this arrow going both directions? That's telling me that we have a possibility of either structure. And what actually occurs, I would say that the actual structure because they're the same indicates it's an average of the two. So I don't have one that actually stands out.
That says actual structure what indicates?
Actual structure indicates it's an average of the two because there's no dominant structure. So I would say that O3 is considered to be a blend of the two resonance structures.
What does that mean?
That means that I think of it like this, it's like if I'm looking at ozone, it's kind of in a state of flux between one molecule might be bonded one way, one might be bonded the other way, and in all of nature I would average that and find them to be somewhere either in one or the other state. But the overall characteristics would be an average of those two states. Okay, so now I'm going to have you do this. Let's see. Let me think of one that'll work. Oh, what's that? I don't think those are... Well, that's a whole bunch of papers that don't belong in there. Let's look at... this should work pretty well. Nitrate ion. I want... Let's see. All Lewis structures, and I want formal charge, and then I want to know best resonance structure, if there is one, or best Lewis structure. The resonance structures, if you can write, we just call them resonance structures when we can write more than one possibility. So a resonance structure really is a Lewis structure. So take your nitrate ion, move to your lab stations, and try to work through this one. When you think you're done, you need to tell me how many structures you have, and I'll tell you if you're done. What ideally should your formal charge be on the nitrate structures? -1, yeah.
Should we have 3 structures?
You should have 3 structures. When you feel like you're ready to talk about it, come see me.
Yeah, we have no best residence structure. 'Cause they're
You
all
have
the
no
same.
what?
Best residence structure,
Why not?
because they're all the same.
What are they all the same about? What's the same about them?
Like formal charges.
The same, and did the formal charge equal the charge of the polyatomic ion in each case?
Yeah.
Okay, how did you change them? Did yours look like this?
Oh,
Yeah.
but I need to put the brackets on, but yeah.
Don't forget your brackets.
Yeah.
Okay.
Yeah.
What about you guys? Did you find a best structure? No. What was your formal, did your formal charge?
Yeah.
Okay, good. Did you find a best structure?
No.
No, you found that they were equivalents?
Yeah.
What was the formal charge on each one?
1 minus.
Okay, good. What's the best structure? There isn't one. What's the formal charge on all of them? 1 minus. Does that equal the ion charge? Yeah, okay, good. Yeah,
So if the formal charge equals what the actual like ion charge is, it's just gonna be like no best structure. Most people.
well, there might be a best structure if they don't, you could look look at the electronegativity, but in this case, you're only dealing with 2 different, there aren't 3, you know what I mean? So you always want to think about electronegativity.
And it's whichever one where all of them are the closest to 0, right? Because if you have like a minus
Or the
5 and a
ion
plus
charge.
3,
Yeah, yes, you put the, at the end, you're looking at the total of charge.
yeah.
Yeah.
But like if you had like a 1 plus and a 1 minus rather than a 5 plus and 5 minus, the 1 pluses would be the ones that would be like the best resonance structure since they're the closest to 0.
Yeah, closer to 0 is better, yeah.
Okay.
But in the end, if you said a plus 5 minus 5, that's a 0. Plus 1 minus 1 is a 0.
Right,
In
yeah.
the end, you have to look at the number. Like in the end, if you had a plus 1 or a plus 5, the plus 1 would be better.
Right, yeah.
Yeah, okay.
Okay.
Caitlin and Evan, you guys didn't talk to me. Or show me what you did. Come on!
Here's what we did.
What did you find?
There was not a best structure.
What was the oh, I'm looking at the wrong
Negative,
thing.
yeah. And then I have the yellow on the back.
Okay, so in each case, your charge, your formal charge equaled the charge of the ion, right? Okay. So one thing I'll just, well, I think we better write this down, actually. I got papers going everywhere. Couple things to remember. Whoops, remember. Look at the electronegativity. Remember we talked about that yesterday and we had to look at it and I forget what we did, but one of them we had to look at it. And then the other thing you need to remember is that in some molecules or ions, not all Lewis structures are equivalent. And we had a couple of those yesterday. One structure is more dominant. So you have to look at your formal charge, you have to look at your electronegativities, all of those things. Now the last thing I want to show you today has to do more with, a little bit more with organic chemistry, and it's something you should just be aware of. We're going to look at something called benzene. And benzene is an organic compound. You guys who take OChem in college will get to know it well. So an organic compound is called an aromatic hydrocarbon, which means, yes, it's made of carbon and hydrogen. Depending upon how it's being used, it's used a lot in pharmaceuticals. Depending upon how it's being used, it may have some functional groups added to it, meaning some other things bonded to the benzene ring. But lots of times this is just called the benzene ring. And resonance is a super important concept when we start to describe the bonding of organic molecules. I love organic chemistry. Like, I get excited about organic chemistry. It's super cool. Hopefully you won't die doing it in college because it's hard. But I want to give you just a little taste of it. Like, if you are, like Simon, if you're really seriously thinking about chemical engineering, think pharmaceuticals. Like, I don't know if that interests you at all, but there's a million jobs and you make lots of money with the use of hydrocarbons and developing new medical treatments and that kind of stuff. But anyhow, when we look at the benzene ring, it is 6 carbon bonded in a ring. And there's 1 hydrogen atom bonded to each carbon atom. So, I'm going to do my best to draw what this looks like. So we have 6 carbons. So we say carbon, single bond, carbon. Then we have a double bond to a carbon, followed by a single bond, double bond. Oh, that's a bad C. Single bond, double bond. So they alternate bonds. And then off of each one of these, the nice thing about hydrogen is it's easy to bond because it only needs to share 1 electron or give up 1. So now what I want you to do, try to do in your notes, is draw the resonance structure for that benzene ring. When you've got it, stand up. I'm going to have to make my second one little. Caitlin, what'd you do in your resonance structure? You put the double bond at the top up here, like this. And then did you alternate? Is that what you said? So then you went C, double bond, C, single bond, C, double bond C, single bond, is that what yours looks like? Do you still have your hydrogens? Okay, is this what y'all did? Okay, good. I'll put my H's out there. So sometimes we'll add something called a functional unit to this. Like out here, instead of H, it might be replaced with OH, which I would have to show a bond here, but anyhow, sometimes your hydrogen is removed and some other polyatomic ion or singular ion is put in there. And when something new is put in, it's called a functional group. Now, there are all kinds of rules about how we sort of abbreviate these structures, and we're not going to learn all of those right now. I'm just going to show you that in the end, or well, first we'll talk about this. So you need to make a note that in a lot of these things, what you've picked up on or should have picked up on is the double bonds are in different places in the different resonance structures. And that's what makes them resonance structures. We don't change anything about the atoms, we just change the way they're bonded. So it doesn't really normally change our formal charge. When we look at benzene, my 3 carbon to carbon single bonds have a bond length of 1.54 angstroms. And my 3 double bonded carbons have a bond length of, it works out to be about 1.34 angstroms. So the actual benzene can be thought of as a blend of the two, just like I talked about with ozone. This benzene ring is commonly showed, like I said, there's a lot of abbreviations of these structures, commonly shown by omitting, I'm going to say omitting the hydrogen and only showing the CC bonds, but it's shown in a different way. It's kind of, let's see, these are unlabeled, I would say. It's kind of like a understood structure. So to me it kind of looks like a bolt without the wings, kind of. It's like, yeah, I'm starting. I have a hard time getting my lines right when I do this. And then it shows just like the alternating C bonds, like that, and there's a circle in the middle. Now, I'm sure there's a much lovelier picture of it in your book than what I'm drawing. The other structure then would be basically the same thing. I'm just going to move my, where I show my double bonds. And the way that this benzene bonds, it gives it like a special stability that we don't find in a lot of molecules. especially organic molecules. It makes it the framework or the basic, like lots of things are made of benzene chains because they're so strong. Literally, like millions of organic compounds have their foundation in benzene, the benzene ring.
Why do they call it benzene, just because?
Yeah, it has to do with the naming rules, which we'll do. If we have time at the end of the year, I'm going to do some of that with you. Okay, I think I'm stopping there today. I have one handout for you with some bookwork on it, and then one little blip you need to read. I'll have you, let me stop this thing. I'll have you work on the bookwork and